Hello everyone, we are the Testing of Sound Dampening group. The group members are myself, Reed Martin, Marcus Pateron, Harsh B, Braden Crook, and Brendan Joyce. Loud noises caused by industrial settings can greatly impact hearing health. Prolonged exposure to loud noises can cause hearing damage, which can be temporary or even permanent. According to the CDC, noise can damage hair cells, membranes, nerves, or other parts of your ear. Our group plans to combat this prevalent issue through our tests and experiments. Our group is testing the thickness of materials for their sound dampening properties, which then can be used to relate the foam thickness to sound dampening abilities. These tests can be utilized to reduce the noise levels created from angle grinding in the machine shop, a problem that has been prevalent in our school. This not only will be helpful towards improving the comfort for those in adjacent classrooms, but also improve safety by reducing the risk of exposure to loud sounds in the machine shop. Our test objective is to determine what foam thickness is optimal for sound dampening in areas of high decibel levels. To do this, we use 3 foam thicknesses: 1/2 inch, 1 inch, and 2 inch. We then took noise readings from varying distances of 1/2 foot, 3 feet, 5 feet, 8 feet, and 15 feet. The key question we look to answer is how can we relate sound dampening to thickness of foam materials?
Background. Creating a noise reduction barrier between loud environments and areas that require low ambient volumes is a common studied problem. Different foams have different noise reduction properties, and likewise, so do different thicknesses. To simplify our tests, the most used foam, polyurethane, was used as our sole subject of this experiment. We tested between different foam thicknesses to understand how it affects the decibel levels. So some prior work that we have seen throughout research and also throughout the workplace, we have noticed that there has been a lot of use of ACT or acoustic ceiling tiles. So those are the tiles that you see in the ceilings in a lot of classrooms, but also a lot of business places. There's a lot at Clarkson. There's also been an in-depth research study about the acoustic absorption coefficient of polyethylene using 2 microphone transfer function method, and that was conducted at the University of San Carlos. And there was also the study of potential of polyethylene foam as a sound insulation for HVAC units or rectangular ducts, which also goes along the same line as the acoustic ceiling tile. You may be asking, what makes our approach different from others? Most other projects and experiments utilize the speaker systems to test their damping coefficients, whereas our group performed our tests in the same environment with the same live variables. Furthermore, majority of the tests and experiments that were conducted by others were for standard rooms such as classrooms or residence halls. We did not find much evidence of tests that were conducted specifically for machine shops or other places with higher decibel levels. Determining the damping coefficient adds an extra layer of information for materials and their properties. It's a simple and quick method for determining which materials have better damping performances than others. This coefficient can be applied to various applications that require a lower sound output. OSHA regulations require hearing protection for sound levels that exceed 85 decibels. Due to the risk of surpassing this level, hearing protection is required while grinding. As you can see here, these are our linear assumption equations, which we use to define the test variable beta. As you can see, Ln is the expected reading of our decibel meter, which is a function of our source sound level, L source, minus the decibel reduction, A of t, which is a function of beta and t, where t represents the thickness of the foam and beta is the decibel loss per unit thickness, which is what we are testing for. So before we can do any proper testing and receiving any results, we made sure to accumulate some sort of simulation or simulated results. Thanks to AI, we were able to create a neural network that allowed us to predict what our data would look like. So as you can see here on the right, our ChatGPT allowed us to create a rectified linear unit neural network, and in the graph shown below, we could see how over time, with the more epochs that the system goes through, or the more cycles that the system goes through, the mean squared error decreases over time, which basically tells us that our model is learning and getting smarter the more it repeats. So as you can see here, we were able to plug in some hypothetical data that allowed us to plot a predicted output of our experiment. Both of these figures depict the expected decibel readings at varying distances and thicknesses. As you can see, there are some minor errors with these graphs, and this is most likely due to some confusion in the neural network system.
Method. Test plan. Our test plan aims to evaluate how the different foam thicknesses reduce sound in a machine shop environment. To do this, a simulation is run with a grinder. We tested each test box at different distances, which allowed us to gather a larger sample of data to improve the accuracy of our experiment. Instead of creating a fully covered box, we made an open top box, which was used to help us save material and expense. Unfortunately, this would adversely affect the effectiveness of the box. So for our experiment design, on the right we could see a graphic of a flowchart of how our experiment went. We start off at the top where we cut our foam panels into 4 even pieces, and then we followed it up by creating the test box. We then used the grinder by turning it on and recording some initial values with the decibel meter, and then after getting our initial ambient noise, we placed the test box on top of the decibel meter so it surrounds it from all 4 sides. We then collected data of this grinder with the foam box around it, and then we turned it off the grinder en route to file our data, and then we repeated this process for all the 3 types of foam and all of the distances that we've used. The required materials to run this experiment are as follows. We needed 3 4.5 foot by 1 foot polyurethane panels at 3 different thicknesses, 1/2 inch, 1 inch, and 2 inch. We also needed a hot rolled steel about 99% iron and 0.75% manganese, Larson Davis Alex T1 sound level meter, and a 12-inch disc sander of 1.25 horsepower, 60 hertz, and 1,794 RPM. Our total cost for this project was $48.74 before tax and shipping. So our process for this project is as follows. The first step is to turn on the grinder and then place a decibel meter at a specific distance from that grinder. You turn on the decibel meter and note down ambient measurements from the decibel meter display. And then after a few seconds of getting those ambient measurements, you place a test box over the decibel meter. You then measure the output readings from the device and then turn off the grinder and remove the test box. You would then write to file the data received from the decibel meter, and then at that point you would repeat steps 3 to 7 for various distances and steps 3 to 7 again for all foam materials. Then you'd analyze the data gathered and create relevant plots. So for the conditions and relevant materials, the machine shop setting can vary majorly with the use of other machines and background conversations which make it difficult to obtain precise readings. A few examples of background noise could be the materials being moved, machines being used, and conversations being held. This in turn means that there are many variables where the control variables are the grinder, decibel meter, and distance. However, this increases the accuracy of our testing by reproducing the environment's natural response. For this reason, the reproducibility factor may be reduced. So for measurement and calibration, an ambient sound level is recorded to provide a basis for the analysis of results, which is followed up by a set of decibel readings within the box while the grinder runs. The decibel meter has a write to file function, which allows for the automatic measurement and analysis of our data. Our schedule. The estimated time frame for this entire experiment was met, which was completed in 1 semester or 15 weeks. The expected schedule for each step of the experiment and its preparations can be followed in the Gantt chart provided. Our risk assessment. The primary risks associated with this setup are high sound levels and fire. OSHA regulations require hearing protection for sound levels that exceed 85 decibels, and due to the possible risk of surpassing this level, hearing protection is required. Since polyurethane and most other foams are flammable and release toxic gases when grinding, catching on fire poses another risk. Due to this, we must ensure that grinding is directed away from the test box and that a fire extinguisher is on hand. These risks are easily mitigated when handled with care, but pose danger when preventative measures are not taken.
Results. The first thing we notice in the results is that the decibel readings not only weren't constant, but they varied quite a bit. The graph here on the bottom is one of the better looking ones we had. This was a test for the 1-inch foam box at a distance of 5 feet. In others, there were random spikes caused by external noises as we were testing in the shop with other people around. To avoid the spikes and use a uniform method of analysis, the highest natural peaks were used as the decibel readings for each test. These are tabulated on the right here and graphed on the bottom. As you can see, there are some discrepancies in the 1-inch and 2-inch tests where the values may not be correct. This could be caused by any number of reasons, as will be discussed later. The control and half-inch tests are more accurate though. You can see how the sound drops off over the distance by following the lines, more so over the control and half-inch tests. You can see how sound drops through the different thicknesses by comparing vertical values. To solve for beta, we use these two equations that were discussed before. With the control values as L source and each test reading as L in, we calculated the beta value for each test before averaging them out to find the experimental value of 6.1 decibels reduced per inch of polyurethane foam. Now that we had our beta value, we plugged that back into the equations along with the control values and test box thicknesses to calculate the theoretical values for each test. These values can be seen in the top right. The graph on the left is a comparison of the measured values and the theoretical values for the half-inch test box. As you can see, the theoretical values follow the same line path as the control values for the test peaks. This is because the equation for sound loss is at a linear approximation. With the theoretical values, we calculated the percent error. The max error was 11.9%, which occurred during the 8-foot test of the 1-inch test box. You can see from the graph on the right how it's higher than the value for the half-inch test box. The average error for the experiment was 3.5%, which is pretty reasonable and shows the accuracy and repeatability of the experiment.
Conclusion. Primary conclusions and outcomes. Our main objective in this experiment is to find a way to relate sound dampening to foam thickness. This result can be seen as beta. Beta in our case was found to be 6.1 decibels per inch, meaning that for every inch of material we add, we gain an extra 6.1 decibels lost. This beta is only applicable for our test, however. This beta would not prove accurate for different materials or different shapes. Nevertheless, this value is still important due to the fact that it answers our main question: how does foam thickness affect sound? The error that could be found in our testing could be from a myriad of sources. First and foremost, the implicit error from the machine and sound meter themselves. Though the error caused by these devices were limited through calibration, there is only so much that can be done to reduce these errors. Along with that, we attempted to have the fewest amount of people in the room with us. However, there were still a few people working within the machine shop during our data collection. The noise created by the use of other machines can be seen as spikes in our graphs. That is why we had the ration that these spikes would be outliers and would be left out of our averages. Furthermore, the grinding that was done by our group was semi-inconsistent. There were moments when the steel rod would kick up and the grinding would cease for a moment before resuming. Finally, the surface on which our decimal meter was placed varied between each test. Though the error is minimum, it's still a source for error within our experiment. For future steps, if our group was to continue with our test plan, we'd make some refinements to our sample size. This would be done by changing the variables of our test environment in the material testing. In future tests, we could run multiple iterations on a variety of foams with a variety of shapes and thicknesses. This will allow for us to gather a greater understanding of how exactly foam dampening affects the sound level of a space. Along with this, we could derive more beta values and cross-compare them with each other to find out which yields the best result. Thank you.